So one of the first examples that we will do to solve some viscous flow problems is the popular, famous Poiseuille flow between two parallel plates. So this flow is based on the following situation. You have two very long rectangular plates that extend to infinity, and you have some pressure P1 over here and some pressure P2 over here, and P2 is smaller than P1, therefore dP by dx is negative. Okay, we haven't said anything about what dP by dx is, so we expect the flow to go in this direction. Now, if you take a cross section here, this is the setup for our flow. This is P1, and this is our P2. And following our standard strategy, for the first step, we're going to sketch what we expect the flow to look like. And in the absence of anything driving the flow, so U equals 0 over here, U equals 0 over here, and in the absence of any effects in depth and vertical effects, there's only unidirectional flow in this direction. And we expect the velocity profile to be kind of curved like this, because if it were linear, we would have a discontinuity in the shear stress at the point, at the center, and so therefore we would have to kind of have some kind of smooth profile. We'll show that this profile is actually parabolic. And for step 2, we're gonna consider a coordinate system. We're gonna place it right here in the center, x, and this is y. The channel height is going to be 2h, so we have an h over here and an h over here. The total height is 2h. And in terms of assumptions, we're going to assume that the flow is steady, Newtonian, constant properties, constant rho and viscosity, and U is not zero, V equal W equals 0, therefore dV and dW are equal to 0. We will also assume that there are no pressure gradients in the Z and the Y direction, so dP by dZ equal dP by dy is equal to 0. And U is only a function of the x direction. We'll actually prove this in a second. So we're going to consider the Navier-Stokes equations in axial coordinates, starting with continuity. This would give us du by dx plus dv by dy plus dw by dz equal to 0. And because v and w are 0, this gives us that du by dx equal to 0, which implies that u is a function of y and z only. However, since we are neglecting all effects in the z direction, it's very, very deep, then we can safely assume that this is just equal to u of y. So the only non-zero velocity component, so du by dx equal du by dz is equal to 0. Only non-zero velocity gradient is du by dy is non-zero. Then we go to momentum, and you agree that we will only need the x momentum equation. The other ones are just going to cancel out. We have rho du by dt plus the advection term u du by dx plus v du by dy plus w du by dz. So the velocity, the x momentum component u is being advected by all three velocity components in the x, y, and z direction, equal minus dp by dx plus mu d2u by dx squared plus d2u by dy squared plus d2u by dz squared. Now we said the flow is transient, so this is 0, du dx is 0, du dy, v du dy is 0, w, du dc is 0, this guy is non-zero, d2u by dx squared is 0 because du by dx is 0 and d2u by dz squared is 0, and that leaves us with just the one equation that says mu d2u by dy squared is equal to dp by dx, or d2u by dy squared equal 1 over mu dp by dx. Now we haven't said anything about dp by dx. We will actually prove that dp by dx is going to be a constant, but this is easily can be easily integrated. So we do one integration, du by dx, you get 1 over mu dp by du by dy, you get 1 over mu dp by dx y plus c1, and u of y is equal to 1 over 2 mu dp by dx y squared plus c1y plus c2, subject to the boundary conditions. BC's u at the bottom of the channel, so that's minus h, is equal to 0, and u at the top of the channel, h, is equal to 0. Each one of those implies at first one 1 over 2 mu dp by dx h squared plus c1h plus c2 equals to 0. The second one 1 over 2 mu dp by dx h squared minus c1h plus c2 equal to 0. Now we can solve for the constants. 1 plus 2 will cancel out c1, and that gives us 2c2 is equal to 1 over mu minus 1 over mu dp by dx h squared. So we're going to put this mu down here. That's c2. And from that, we conclude that c1, so substitute into equation 1. This will imply 1 over 2 mu dp by dx h squared plus 0 minus 1 over c1h. We're going to show that it's 0. 1 over 2 mu dp by dx h squared equals 0. These two cancel out, and that implies that c1 is equal to 0. Finally, u of y is equal to 1 over 2 mu dp by dx y squared plus 0 minus 1 over 2 mu dp by dx h squared. So we combine the two to get u of y is equal 1 over 2 mu dp by dx into y squared minus h squared, y squared minus h squared. And indeed, if you plot this from minus y to y, this is x and y, you're going to get this nice parabolic profile with the maximum occurring at the center line. Maximum velocity at y equals 0, we get the maximum velocity. We haven't said anything about dp by dx. So let's show that dp by dx is a constant. If we calculate the flow rate q going through the pipe, that's the integral from minus h to h of u of y dy. And that's the integral from minus h to h of 1 over 2 mu dp by dx into y squared minus h squared dy. Now dp by dx is a function of x only. Okay? dp by dx is a function of x only, and you can show that from the other two equations where you can show that the pressure is just a constant plus a function of x. If we assume no hydrostatic variation in the y direction or neglect that because we've neglected gravity. So this thing can come out of the integral, and the result of this integral would be 1 over 2 mu dp by dx, integral minus h to h of y squared minus h squared dy. And if you carry out the integration over here, you will get so 1 over 2 mu dp by dx, and you will get times minus 4 over 3 h cubed, and you will have minus 2 over 3 mu dp by dx h cubed, and that is q. Now we know that q, the volumetric flow rate, is constant throughout any section of the flow. And because mu and h are constants, then this necessarily means that dp by dx equal a constant. Okay. Now in practice, you think about it, you are setting a pressure at the inlet, and the flow is probably exiting to atmospheric pressure, and that pressure gradient, which points in which is negative, hence the negative sign over here for a positive flow rate, because dp by dx is a negative quantity. So this gives you a positive flow rate. So that's what's driving the flow. Okay, and this essentially gives you the second type of problem that we will be dealing with. Last time we dealt with the Couette flow problem, where one of the plates was moving, causing the flow to move. In this case, right here, it's the pressure gradient that is causing the flow, causing the fluid to move. Now, once you have the velocity field, you can do all sorts of fun things with this. For example, you can calculate the shear stress at the wall, and you can get an idea of what the shear stress looks like. So without even punching any numbers, if this is our velocity profile, we expect the only non-zero shear stress, is tau yx. So again, this is x, this is y. We're looking at y lines of constant y, or y faces, and the shear stress is going to be in the x direction. Now, what do we expect here? We expect that the shear stress, so what is tau yx, is mu dv by dx plus du by dy, which is mu du by dy. So we expect when du by dy is 0, the shear stress is going to be 0, and indeed du by dy over here is 0, so we expect to have 0 shear stress over here, and maximum shear stresses near the walls. Now the direction of these shear stress is going to be dictated by whatever sign we have here. So if you do mu du by dy, what is du by dy? So we have mu times 1 over 2 mu dp by dx, okay, and that's times 2y. So the two cancel out, mu and mu cancels out, and we get y dp by dx, and I'm gonna write this as minus y times minus dp by dx, because dp by dx is negative, minus dp by dx gives you a positive quantity, and this minus y is gonna determine if you are in the positive y direction, then tau yx is gonna be pointing in this direction. So we have tau yx over here, and it goes all the way to 0, and then it switches signs, and that is consistent with our convention for the sign of the shear stress. Okay, so essentially a fluid of larger y acting on a fluid of lesser y. Now once we go below this line of y equals 0, then y becomes negative, so this guy becomes positive, and then it points in that direction.